Hey guys, welcome back. This is Mr. Kelly at Kaiser Slaughter, and we're going to learn about financial modeling today. And a lot of financial problems, they're exponential, so that fits nice in this unit. So let's write down a couple things. Remember, pause the video as you need to. You might want to pause it right now and just write down these values, and then listen to me talk about it because that's cool. But the first thing we're going to do is recognize we have three different formulas that basically permeate all these financial problems. The first one deals with compounding interest that is periodic. Okay, now just so you recall, you put money in the bank. The bank basically borrows money from you. You put it in the bank, and they pay you interest. And then they take that money and they loan it to other people, and they charge them interest. But that's how a bank makes money. We have three different equations that we're going to use here as we figure out what the interest is. It depends on how they compute it. The first way, periodic, means they do it so many times per year, and they'll have to tell you. So if they say quarterly, it's 4 times per year. If they say monthly, it's 12 times per year. So we might want to write some of those down. Okay, so I put some that are important over here. Quarterlies, 4 times a year. Monthly, 12 times. Daily, 365 times, not counting the leap year. Why do I sound like a robot? And then semi-annually would be 2 times a year. But they could give you, maybe they say 5 times a year. I don't know. But whatever they give you, that's what those values mean. And we're going to have to put it in the formula. So when it says that it's compounded quarterly or monthly or daily, that's periodic compounding interest. And so this is the formula we use. Go ahead and write this formula down, and I'll go through what each of these letters represent. So A is always going to be the amount of money that you have at the end of this is like the end of the problem. Like, how much money do you end up with? So if I put $100 in the bank, how much should I end up with after a year? That's what the value A represents. Years are measured here with T, so that's time, but that's the number of years. P is the principal. It's how much money you start with. So when you put money in the bank, you invest money. If you invest $100, then the $100 is the P. The interest rate is what R stands for. R is the rate, and you have to write that as a decimal. So if you have 8%, it's 0.08 that you put into the formula. N is the number of times that the interest is compounded per year. So maybe you say like look over that way, because I wrote down a whole bunch of them over here. But that's going to be our major clue that we have to use this formula, is that you're reading the problem and it says one of these words like quarterly, monthly, daily, semi-annually, etc. So the next type of problem is going to involve continuous compounding interest. Now, continuous means it doesn't stop. So periodic is like, oh, we have all these different, like we have these breaks in time. I'm going to do it every 4 times per year. Okay, so it's 4 times, you wait 3 months, you do it another time, you wait 3. Okay, continuous is if you're doing it instantaneously at every single second. And we're going to talk about that later on in this lesson. But if it tells you we're doing continuously compounded interest, then guess what? We're going to use a different formula. We're going to use A equals PE to the RT. If you've heard of Pert shampoo, then that's how you remember that. Continuously shampooing your head, maybe? I don't know. That doesn't make sense to me either. But continuous compounding interest, A equals PE to the RT. The P is the same, principal. E. Whew. Now, this E, it's not the E from, what was that show? Entourage? No, we're not doing that. This is a value. It's very similar to, let's say, like pi. You know how pi has a value? It's 3.14. Well, E has a value, and it's 2.71828, 1828, a lot of 8s, 459, etc. And it keeps going. It is irrational. It's just like pi. It happens that this ends up in a lot of our mathematical formulas, and you're going to find a couple in this lesson. So if it says that the interest is compounding continuously, we're going to use this formula right here, plug it in, figure it out. And lastly, the percent increase or decrease, we already know this one. We have an initial value and a multiplication factor here that we multiply by, and so a b to the x, we know how to do that already. Okay, so some of the problems will involve that. So right now it's just time to practice, identifying which formula is appropriate. So let's look at the first one. We're going to deposit $1,000 into an account that pays 6% interest compounded continuously. So the first thing I'm going to do is I'm going to highlight this part right here, because that is the most important part. It's compounded continuously. So that tells us we're using the second formula. A equals, I'm going to write this down, A equals PE raised to the RT power So in this particular problem, we have to identify the principal. Remember, E is this number up here, 2.7182. R is the interest rate. We have to write it as a decimal. And T is the time. So here's T. I'm going to highlight these things here. Well, I'll underline them. Those are all of our pieces of information that we need. So the amount of money in this problem is going to equal, we have 1,000, and we're going to multiply by E raised to the interest rate, 0.06, times the time, which is 5 years. So we can put this all in the calculator. You don't believe me? Here it is, 1,000. And then look, above, all right, here's the 4, and then this is called the natural log. All right, E, it's technically called the natural base. That's what we're dealing with right here. But the natural base here, E, we have to use the second button. And look, the little tiny E pops up. So then E we're going to do to the 0.06 times 5. All right, we hit the enter button and we're going to get $1,349.85. So I'm just going to leave that right here while I copy that down. Total amount is $1,349.86. Mr. Bean will come back and check for that extra penny if you don't round properly. That is the answer to this problem. Does it make sense? We should always do a does it make sense test. If you invest $1,000, does it make sense that after 5 years you have $1,300 if they're paying you interest? And that does sound reasonable. Okay, it's in the ballpark, so I'm going to be okay with that one. Let's try the next one. So the next problem is you deposit $2,000 into an account that pays 4.8% interest. And here's the key. Quarterly. Now, as we said before, if we're going to do periodic compounding interest, they're going to be keywords: quarterly, monthly, daily, semi-annually. Okay, so this says quarterly, so that means 4 times a year. So we're going to use that formula right there at the top, the very first one. Most ugly formula, but, you know, here it is. 1 plus R over N raised to the NT power. So I'm going to plug in all the values here. The P is the principal that you start with. So that's going to equal 2,000, because that's what they tell us we invest. 1 plus the rate. So the rate here is 0.048 divided by N is the number of times per year, which would be 4. And we raise that to the NT power. So it would be 4 times the number of years, which is 10. All right, let's put that all in the calculator. So as I put this into the calculator, just make sure that you're, using parentheses, right? Order of operations. We have 2,000's principal. We're going to divide these two. It will do order of operations, so I don't need parentheses. But if you include them, that's okay on the inside. And it's raised to the 4 times 10, or the 40th power there. And we get about $3,000. Now, brain check again. Let's bring that back down. Brain check. Does that make sense in this problem? If we have $2,000, we invest it for 10 years. All right. That's approximately equal to $3,222.93. That's what the amount would be. Does that make sense? Is that reasonable? That is reasonable, because you invest $2,000 and you leave it in the bank for 10 years, you're going to make some money on that. Okay, the last one. Okay, well, guess what? We're going to use this last formula here. This is one of our formulas we already know, percent increase and decrease. So you have a home that's worth $100,000, and it's increasing in value at 2.5% each year. So it's a percent increase of 2.5%. So if you remember how to do this, we're going to do the value of a house, T, given the time. I'll use V of T, but you can use F of X or whatever. It equals 100,000. All right, now we're doing a 2.5% increase. So remember, you got to add that to 100%. That's 102% of what you had before. So writing that as a decimal, we get 1.025, and we're going to write that down. Here's our model. Okay, so it says write a model. Boom. And then find the value of the home after 20 years. So that means we're just going to plug a 20 in. So 100,000. Let's put this all in the calculator and figure this out here. Easy. By the way, I already had it down here. That's sneaky. Sneaky. So this $100,000 house after 20 years, we're going to say V of 20 is going to equal $163,861 and 64 cents, approximately. Add a dollar sign to make everybody happy, and we'll circle it. All right, so that's how we use our three financial equations here to help us out. Now we're going to look a little bit at where this E comes from. Now, take this out. What if we got, let's start with this periodic function. As we start, let's talk through it. You start with a bunch of money, and then you're raising it. There's a percent increase, and you do that so many times for so many years. So as whatever the rate that you're given, if you do it 4 times a year, you need to divide that rate by 4, because you're going to add interest 4 times a year, okay? And then, you know, it's 4 times, you're going to do that for 4 times per year times the number of years. So let's look at this little chart right here. Let's look at this part of the equation here. We've taken the rate out of it. What happens as we do it more and more and more? Okay, so if you do it 1 time per year, or if n equals 1, you plug a 1 into here. You get 1 plus 1 raised to the first power. That's just 2. And as we increase this, and we keep going from 1, and maybe we go to 10, notice how the value changes a little. So it's 1 plus 1/10 raised to the 10th power. That's 2.59. And then we raise it to the 100th. That'd be 100 times, 100,000 times, 1,000,000 times. And so we say, as n goes to infinity, as we do this instantaneously, it means every single second, because you're taking the whole year and you're dividing it up into every, like, I don't even know how many, like a million, billion, like every, and you're dividing the rate and multiplying it. Anyways, this whole value here approaches 2.71828. And that's where the value of E comes from. Okay, so, you know, take R out of this and just put a 1 there, and, you know, see what happens as it goes. And this is the value we get there, an E. So these are essentially, this is what happens. This thing goes to an E, and that R kind of pops out, and we get this equation there with some manipulating. But that's where it comes from. You have to know that this value right here, that's irrational, and we can just figure it out in our calculator. So let's pull the calculator up and do some of these problems. Like the first one is, the first one's not calculator. The next ones are. Hold on. Before we get to the calculator ones, we're going to manipulate these a little bit. It's the same rules for, exponent rules that we had before. The rules are, if they're side by side and you have a common base, you can add exponents. So we're just going to add these exponents right now. This is going to become e to the 2x plus this exponent, which is 5x minus 1. So this reduces to 7x minus 1 because we combine like terms. Done. Okay, we're just simplifying these. Next one, we have an exponent of 2 on the e. So this is going to get, oh my god, so the rule for exponents is you multiply. So to multiply here, it's just going to be 5 times e to the 2 and then 5 minus 2x. That's what multiplying is. So if I reduce that, I say reduce, if I simplify that, these are the right words. I get the 5 and then I distribute this to each of the top part and we get 5e to the 10 minus 4x. All right, last one, number 6. If I'm going to simplify this, you know, the coefficients, we just treat numbers like numbers. As Mr. Bruss says, you treat numbers like numbers. He really says that. So 10 divided by 5, that's just 2. And then we have x. We have to do x. Ooh, I forgot my e. 2e to the x. And then we got to subtract here because we're dividing. So it's minus x minus 3. And make sure you use parentheses around that because you got to subtract the whole thing. So now when I simplify this, I'm going to get 2e to the, what do we get? X minus x plus 3. So this simplifies to 2. X minus x kind of cancel. And we get 2e to the third power. That's kind of crazy. Make sure when you're doing those, you just check the answer sheet. Make sure that you're, simplifying correctly. One of the things that's not in this part, but it is on your homework, it says you can only have positive exponents. So if that was a negative 3, we'd put the e to the negative 3 in the bottom of a fraction and make it positive. All right, now the calculator part. I was so excited about the calculator. So excited. All right, e to the third. Now, as I said before, the e is right here above the natural log. It's called the natural base. So we hit second, and then, boom, you're already in the exponent because it knows that we do a lot of problems with the exponents. So we're good with that. Okay, that's where we get that answer right there. What do we got? E to the negative 0.2. Yeah, there are some of these on the mastery check, and we're checking to make sure you're not using the minus. You have to use the negative. So I'm going to do negative 0.2, and you just hit the button, and it's approximately 0.818. We're going to go out 3 places, so this is going to be 8, 1. Instead of 8, that's got to go up 819. So this is 0.819. Is the answer negative? No. Because remember, this just means this. And that's positive. All right, so we don't have a negative answer there. All right, we have 2 more that we're going to look at. Number 9 is another way that we take that number E. And, it shows up a lot in mathematics. So here's an example. We have the population of a country called New Beanland. Okay, New Beanland was 40 million in the year 2010 and has grown continuously for the years following. That's kind of where we get that E working out. The population in millions of the country T years after 2010 can be modeled by the function P of T equals 40E to the 0.027T, where T is greater than 0. Then they want you to find the average rate of change. Now, I took this type problem. It's very similar to one that I found on like one of those standardized tests that you take. A lot of times in those problems, they're going to give you the equation. So I'm going to write that down. They do give you the equation a lot. You're not expected to memorize these, but you are expected to know how to use them. So in this situation, we're starting with 40 million. I'm not going to write the number 40 million out. I'll just write 40, and I'll know my populations in millions later. But this is years after 2010, and they want to know the average rate of change from 2010 to 2015. So we know that T is going to equal 5 here because it's been 5 years. So we need to find P of 5. All right, we're going to plug that into the equation. I'm just going to write it out here so that everybody's happy with me. I don't do any work in my head or in my calculator without showing. And when I put it in my calculator, I get 4578. All right, so that's the value of P of 5. So let's write that down. P of 5 equals 4578. And of course, we know that that's in millions of people, so 45 million people. They want to know the average rate of change. So if we started here and we ended up there, and it's been 5 years, right? So this was 5 years. So how much has it changed each year? What do we have to do to find that answer? You are correct. We need to divide by 5, but we have to find the difference first. So it went from 40 to 45. We want to find how much it's changed. So I'm going to take that 4578. I'm going to subtract off the 40. Very cool. And it leaves me this number. That's how much it's increased. And if we want an average rate of change, that's another word for slope. We can use the slope formula. We subtract the y's, we subtract the x's, but we just need to divide by 5 because it's been 5 years, and it tells us 1.156. So let's write that down. We're going to get 40, ooh, that's ugly, 4578 minus 40, all divided by 5, is going to give us our average rate of change, and that equals about 1.156. Now, let's put a unit on this. So 1.156 millions of people, ooh, let's make room. So 1.156 millions of people per year. Done. We answered that question. Awesome. I hate that box though because it goes in the next problem. So let's do the last problem. Scientist places 7.35 grams of radioactive element. Now you know radioactive things, they decay. And we kind of talked about half-lives before. But as I said, after D days, the number of grams of the element is given by this function. As I said, they give you the functions a lot. So then we just have to figure out which of the following are true. This is multiple choice. Sorry, multiple choice. So which one of these are true? We have 6 different options. The approximate equivalent equation is, notice how they got rid of the exponent up there. All right. We have 2 options for that, where the base changes. And then the base of this form can be interpreted to mean the element decays so much per day. And then they talk about a percent. So, really we need to figure out which one of these matches does A or B match with what we have up here? And then based on that, look, these are basically different interpretations of the exact same thing. So we will look at those in a second though. But first thing I'm going to do is I'm going to go back up here and I'm going to try to rewrite it. So R of D, it's the amount that's left over after it's decayed so many days. D stands for days here. So we got 7.35. I'm going to rewrite this as 1/2 raised to the 1/2 times D, right? Isn't that the same as dividing by 2? It's like half D. And then I'm going to rewrite that as 7.35 times 1/2 to the half power, and that is raised to the D power, right? Because our rules for multiplying, our exponent rules, powers to powers you multiply. Well, these have been multiplied, so that means it was powers to powers. So really what I need to do is figure out what is 1/2 to the 1/2 power. So that'll give me R of D is going to equal 7.35 times, let's break that calculator out. I need 1/2 to the 1/2 power. So 1/2 raised to the 1/2 power. Remember, that's also the square root. We could have just taken the square root. I know, right? 0.707. That makes me happy. You know why? Because we have 0.707 shows up in our answers there, raised to the D power. So that means that B is correct. An equivalent equation, approximately, because that's irrational, so it's approximate. But we get R of D equals 7.35 with a base of 0.707. Now, let's see if either one of these are true. Okay, now the base here, I know C is not true because the base in that one's wrong, and I know E is referring to 0.25 as well. But the base of this form of the equation can be interpreted to mean the element decays by 0.707. Is that how much it decays? No, that's not true. Because remember, it's always the difference from 1. So the difference here would be 0.293, right? Because 1, you got to go down 0.293 to get to 0.707. It's how far you are from 1. So this is not true. That one is not true. The last one, F, the base of this form can be interpreted to mean about 70% of the element remains. That is correct. We have about 70% of this, and then you do 70% of that, and then 70% of that. So in this multiple choice question, we have B and F are the correct answers. Okay, so that's it. This has a lot of different word problems. Make sure that you're checking your answers on the practice. This is Mr. Kelly in K-Town. Remember, it's nice to be important, more important to be nice. See ya!